All right. Now, we spoke about ferromagnetic items, and let's just quickly recap. If I had a piece of iron, which is ferromagnetic, and if I placed him, oops, that's probably shouldn't be doing that. That's going to scratch the surface of my very strong magnet. Now, we've got a very, very strong set of magnets here, and there is definitely a strong magnetic field. I pull that off. That's quite a strong magnet. So my piece of iron very much likes to align itself in that magnetic field. Now what we've got here is a piece of aluminium. Now aluminium is not ferromagnetic, it's paramagnetic. So it has a weak response. And so if I bring in my aluminium, what you'll find is that once it's allowed to settle down, like a good student at the start of a class, it's going to slowly align itself into the very strong external magnetic field. Let me just bring it back a little bit so that they're not touching. So it's aligned itself like the iron would. Okay, so you need to imagine that there are really, really strong magnetic field lines going through here. I don't know if I'd be able to show this with the iron filings, but there's definitely very strong fields going between the two unlike poles in our gap magnet here. And we can increase how far apart they are, but this is a good size. So it's aligned itself, but very, very weakly. As I said, if this was iron, as you saw, it snapped itself right straight to the face of the magnet, often quite violently. And I've, scratching the magnet, not a good idea. And so we can rotate this around, and it's very weakly following the magnetic field. Okay, now that's paramagnetism, and that's exhibited in such items as aluminium, uranium, platinum, and oxygen. Liquid oxygen will actually do that as well. Now we don't have any liquid oxygen here, we'll have to just watch some YouTube videos. The next one is quite strange. This is diamagnetism, and diamagnetism is very weird. And we don't see it that often in nature, but glass is diamagnetic. And what it does is, rather than joining up with the magnetic field lines, it's going to oppose. So the glass is actually now aligning itself horizontal. It's trying to find the weakest orientation. It wants to oppose that magnetic field. It does not want to join in with it. Okay, and if I slowly rotate it, again, this is a very weak effect. We don't often see it in nature, but you can see it's rotating its way around. It does not want to help or join in with the magnetic fun. Okay, so this is the very strange phenomena where an object, the domains will align themselves to oppose the external magnetic field rather than align with it. This is obviously the science behind superconducting levitation. What happens is a lot of objects, when you cool them down to very, very low temperatures, this phenomena occurs. You're almost locking in those domains and preventing them from aligning. So there's obviously a lot of cool videos of magnetic levitation. Graphite does this very, very well. You can get very well engineered sheets of graphite, which can, if the magnetic field is strong enough, you can have it hovering or levitating above the track. And I'll show you at this point of the lesson, obviously, I would be showing you some very cool superconducting materials that demonstrate this effect. Most materials don't become most metals don't become superconducting until they're very, very, very cold. And when they get down below a certain critical temperature, they become superconducting, and then they will exhibit this very strange phenomena. Now, that's the three main types of magnetism. So I say main, obviously the ferromagnetism is the big one, which we're going to be dealing with for the majority of this course. But just please recall there are some two strange types that are not ferromagnetic. You've got paramagnetism, which is very weakly interacting, and then your diamagnetism, which is the very strange one. Okay, there's not really much that can be asked about this in the course. It might pop up in a comprehension section where you have to explain the domains and magnetic fields and things like that. So we'll leave it there.